Okay, we're on chapter 2. We got into some calculations last time about waves, photons, and how energy is transported. Uh, we had our C is equal to our wavelength times our frequency. Um, C here is the speed of light, which is 3 times 10 to the 8 meters per second. Obviously, lambda is the wavelength. When you do use this equation, as we talked about, you do need to make sure it is in meters, so everything properly cancels out. The new here is the frequency, and frequency is units typically of reciprocal seconds are a hertz. And again, one reciprocal second is the same as a hertz, so it is a one-to-one relationship between those. So this allows you, if you know the wavelength of the photon light that's coming off or the frequency of the light coming off, you can figure out obviously the opposite thing there, as C is a constant. We also talked about the energy associated with those photons of light, and energy is equal to H times the frequency. H is Planck's constant, 6.63 times 10 to the minus 34 joule seconds. This also allows you, obviously, if you know the frequency, you can figure out the energy associated with that photon of light. We also can kind of tie both of these equations together, like we talked about. And if we solve for the frequency in the first equation, that is C divided by the wavelength. And if we substitute that into this equation, we get E is equal to hc divided by the wavelength. So what this allows you to do is, if you know the wavelength, you could also calculate the energy associated with that wave. And also you could do the energy associated with the wave if you know the frequency as well. We talked about sort of Bohr's model of the atom, and again, it's that planetary model where electrons are going in pretty little circles. Again, we have different energy levels, which is the N, which is actually the principal quantum number. And the principal quantum number is basically the energy levels. And they do run like N is 1 through 7. N equals 1 is the ground state. That is the lowest in energy, closest to the nucleus. Anything above that is considered an excited state, higher in energy, further away from the nucleus. We also talked about the energy associated with an electron as they transfer energy levels. So again, as they transfer energy levels, as they may go, say, from a higher energy level to a lower energy level, that's going to be sort of an exothermic process for the atom. It's going to give off that energy in the form of a photon of light. Remember that if that photon of light sort of falls in the visible part of the electromagnetic spectrum, we'll see sort of a color, kind of like what you saw the other day. Again, it could fall outside of the visible spectrum, and you wouldn't obviously see a color associated with it. There's a certain amount of energy associated with that, and that's the change in energy is minus 2.18 times 10 to the minus 18. I feel like I ran out of room on that right. I'm going underneath it one more time there. Try so I clear those other numbers. Times 10 to the minus 18 joules. 1 over the final energy level minus 1 over the initial energy level squared of where that electron is. This is sometimes referred to as Rydberg's constant, and that is a constant value. Once again here, as maybe you did in some of your calculations or saw in some of your calculations, and as we talked about, it is important that when you do calculate energy, that if it is a negative value, you leave it as a negative value again, because that implies that it's an exothermic process happening. Obviously, if you get a positive value, you should keep it positive. That implies the opposite effect, which is an endothermic process. That's really the process that's occurring when the electron's actually getting excited from a lower energy level to a higher energy level. Energy has to be put into the atom. That's going to excite those electrons to a higher energy level and so forth. This does tie into these equations here as well. So that's the same. E is equal to H times the frequency, or Hc over the wavelength. So again, those are all basically tied to each other. Any questions on that there? Yeah. I personally used a rounded number. If you want to use the number that was in the lab and stuff like that, which is pretty much 2.179 or something like that, maybe, or 8 or something like that. So it's pretty close to it. I personally, a lot of times will use the 2.18, but either one's perfectly fine. Yeah. Other questions? And again, that is sort of a constant value, again, known as the Rydberg constant. All right, so I think we laid up right around an example that does all those type of calculations we were doing the other day, I think. All right, unless I pass that. There it is. All right, so yeah. So let's talk a little bit about this before. I don't think we went through this part of it, though, just to make sure. A reminder that the model, as we talked about, does correctly, Bohr's model is sort of planetary model, does sort of correctly fit the quantized sort of energy levels that we see in the hydrogen atom, like you saw in the hydrogen lamp that you looked at the other day. Again, the idea there is electrons could orbit. And again, as we talked about, the idea of quantized energy is the sort of idea of the staircase sort of approach that, again, as electrons either gain energy or lose energy, they will gain or lose enough energy to fully sort of transfer from whatever energy levels they're moving from to make it to the next energy level. That's also why, for example, in the lights that we saw there from the elements, because they are quantized energy, you see these specific lines at specific wavelengths, because if that element has an electron that's going to always say transition from like the fourth energy level to the second, it's going to take the same amount of energy, obviously, to go do that transition in that particular element. That photon of light that comes off will have a certain amount of energy, which will correspond to the same wavelength all the time, and you'll see that specific line sort of happening. Now, electrons become more tightly bound. Its energy becomes negative relative to the zero energy state of that free electron. So as electrons are brought closer to the nucleus, energy is released from the system. And again, that only could happen if those electrons drop energy levels to come to a lower energy level, which is closer to the nucleus. Again, the atom's going to have to sort of give up that energy in the form of a photon light. As I mentioned before, Bohr's model is incorrect. It does not sort of hold up as you go with things that have more than one electron. So as you move away from something like hydrogen that only has one electron, its model doesn't really move really well. And as we'll talk about shortly here, electrons, again, do not really move in these circular orbits around the nucleus. As we'll talk about, basically, we don't really know exactly their movement and how they are moving. And it's definitely not in this sort of planetary model that Bohr described. All right, so now that's that exercise here. So why don't you take a few moments here, and what we want to do on these is let's calculate a bunch of things for each of these just to make sure we understand how to do those calculations. So for A, B, and C, why don't we calculate the energy? Why don't we also calculate the wavelength? And why don't we also calculate the frequency for each of these? So why don't you give it a go? Again, the first one is a transition from the fifth energy level to the second. Next one is a fourth energy level to the second for hydrogen, and third to second energy level. So for each of those transitions, calculate the energy, the wavelength, and the frequency associated with that electron transitioning. Take a few moments there and work through each of those. All right, so let's take a look, see how you're doing here. So we got a few different transitions here in hydrogen. So we'll start with maybe the first one here. So we're going n is equal to 5 to n is equal to 2. So obviously we're going from higher energy to lower energy here. So obviously in this case, calculating the energy would be the best route to start with. We'll use our equation here. 1 over n squared final minus 1 over n squared initial in this case. Obviously, this is our initial. That is our final. So our energy here for this electron, 2.18 times 10 to the minus 18, which is Rydberg's constant, and a constant there. 1 over our final, which is basically 2 squared, minus 1 over our initial, which was 5 squared. And that is going to get us here. About 2.18 minus 18. And that's going to get us something like 4.58 times 10 to the minus 19 joules. And that is going to be negative in this case, right? As we should end up with a negative number. That also makes sense. Again, we are going from higher energy level to lower energy level. So the change energy is negative. It has to release that amount of energy to allow the electron to drop to a lower energy level. Question on that one there? Yeah. I think that's fine. On my calculator, I got 4.578 times 10 to the minus 19. So I think you're fine. So you got 4.57. Yeah. Was that? If you, I'm sorry, you got 4 point what? 4.57. That's okay. Yeah. I got that on my calculator as well. I got 4.578 is my next number. So that's why I rounded the 7 to an 8, if that makes sense. Did you as well? Yeah, no, that's fine. That's it's all good. Yeah, it's all good. I use it around a number because there's just too many digits for me. Honestly, either one's fine. Yeah. I'm trying to think. I think the one I give you is 2.18, to be honest with you. So, but if you want to use the 2.179 or 8 or whatever it is, it's fine. It's all good. Same thing with the speed of light, by the way. I use personally 3 times 10 to the 8. People nowadays like to use the 2.9979, type number. So it's all good. Everybody would get credit. Nobody would get, unless I'm in a really bad mood, everybody gets zeros. No, I'm just kidding, but no, you'll be fine. You should be fine. So if you laid up 4.58 or 4.57 in this case, you times 10 to minus 19, you should be fine. Also, again, obviously, you do need the negative as we again are transitioning downward. It should be exothermic. Your question. That would be it would probably be okay as well. Again, that's why, for example, on the lab, it's like take it to 2 decimal places and stuff like that. So, um, you know, I don't know if you would strictly use maybe what's in the parentheses as it might be considered more like an exact number because you're going to be exactly on that energy level or not type of thing. So anywhere in that ballpark, I think you'll be okay. Yeah. And obviously, if the instructions say to give it to however many decimal places like the lab, just make sure you follow the instructions. Other questions on that? All right, so now that we have the energy, we actually have 2 options to get the other 2 things. We could use our, again, formulas, either one of these. So you can really go after either one first if you like, whichever one you prefer. I personally, in this case, I'm going to roll with this one here and just shoot for the frequency next. And if I rearrange that, obviously the frequency in this case is going to be E divided by H. Again, just dividing that to the other side, right? Remember, as we also talked about at this point, although we definitely want to keep the negative here for the energy, we do want to get rid of it in this calculation. Again, you should not end up with a negative frequency or wavelength. It'll still be the same number, whichever number you're rolling with out there in the audience, however you rounded it there. So we'll take that divided by, again, Planck's constant, which is a constant value, minus 34 joules times seconds. When you do that, the joules are going to cancel out, and that's going to leave you reciprocal seconds, which is a unit of frequency. And just not to confuse anybody else, I'm rolling with the whole number on my calculator, not the rounded number. And dare I say, I'm going to go 2 decimal places, 6.90 times 10 to the 14 reciprocal seconds in this case are anywhere within plus or minus, one of that last number. So you should be in good shape. Any questions on that there? Now, again, you still have really 2 options to get the wavelength. You can roll into here if you like, because you do have the energy. You also can, at this point, roll the other sort of formula that we saw, which is the speed of light is equal to the wavelength times the frequency. So why not? Since I just wrote it, I'll go that way. So the wavelength here is going to be c divided by the frequency. So again, I'm going to use the 3 times 10 to the 8 meters per second. If you use the 2.997, you're good. And we're going to divide it by 6.90 times 10 to the 14 reciprocal seconds. Here, the seconds are actually going to cancel out, and the answer I'm going to get is actually going to be in meters. Yeah. What's that? The 4 point. Here? Yeah, so it is negative for the energy, and you should keep the negative, but you should get rid of it when you use it for the rest of the calculations, because again, you really can't have a negative frequency or a negative wavelength. So the simple answer is just kind of get rid of it when you're going to use the number to continue on and calculate those other two things. Yeah. So, but you definitely should, as we've been talking about, keep it for the energy value, the negative. Yeah. 6.9 to the 14, I think, yeah. That's feels like a lot of zeros to count at this late in the afternoon. 4.35 times 10 to the minus 7. These are meters. Since we want nanometers, remember that nano is 10 to the minus 9, so that means in 1 nanometer, there are 10 to the minus 9 meters. Also remember that the 10 to the minus 9 is 1 times 10 to the minus 9, right? That's basically what that means. So very badly written M there. So I'm going to convert that there. So 4.35 times 10 to the minus 7 meters. We're going to go 10 to the minus 9 meters on the bottom, or 1 times 10 to the minus 9, 1 nanometer up on top. That's going to give us a 435 nanometer type of situation. Maybe a violet type color there in the visible part of the spectrum. Any questions on any part of that one there? Yeah. Yeah. So again, we want to kind of keep the magnitude of the energy value that you get, but you do want to kind of get rid of the sign as you go forward and make sure it's positive as you go forward and calculate frequency or wavelength. Yeah, all good. Yep. Okay. All right, let's take a look at the next one. That was 4-2, I think. Yeah, if I'm not mistaken. So initial 4, final 2 will start the same way. Change in energy equals minus 2.18 times 10 to the minus 18 joules. 1 over 2 squared minus 1 over 4 squared. And that's going to get me here. Again, I'm just going to go 2 decimal places. Seem fine for the lab, so why not? 4.09 times 10 to the minus 19 joules. Again, we do end up with a negative value for energy, which does, again, make sense as we're going from the 4th energy level to the 2nd. Again, we're dropping that electron in energy. Atom has to give off that energy in an exothermic, again, negative type number. Again, we have our options, so why not just mix it up a little bit here? We'll go with, we'll shoot for wavelength first. Why not? We'll go that way. So if you chose this way to do it, just to be different, I suppose, we go with E equals hc over the wavelength. That means the wavelength is equal to hc over the energy. These two guys basically switch places. When you do that, multiply the wavelength to the left, divide the energy to the right. Bless you. So you can multiply that to both sides and then divide that guy back over to the other side. All right, so both of these guys up on top are constants. So 6.63 times 10 to the minus 34 joules times seconds. And 3 times 10 to the 8 meters per second divided by our energy, which once again, we're going to get rid of the negative and leave it. Joules will cancel, seconds will cancel. That's going to leave us meters left over. And that's going to give us 6.63 to the minus 34 times 3 to the 8 divided by 4.09 to the minus 19. Definitely, again, want to make sure you're using your exponent button. That's going to give us a wavelength in meters of 4.86 times 10 to the minus 7. Once again, converting that into nanometers, 10 to the minus 9 meters is 1 nanometer. Those guys are going to cancel, and that's going to get us to 486 nanometers in this case. Maybe something bluish. At this point, we can get our frequency. We could get our frequency the same way. We could still also, if you chose to, use this one to get the frequency now that we have the wavelength. Obviously, a reminder that if you choose this one at this point, you need to roll with the meters one, so everything cancels out correctly, not the nanometers one. Otherwise, you won't get the right answer. I'll just go into this one like we did last time, and we'll go E is equal to H times the frequency. That means the frequency is E divided by H. Once again, here getting rid of our negative on it and dividing by here Planck's constant. Once again, joules canceling out, leaving us some reciprocal seconds. We will end up with, that's not the right number. Take that number there, I think. And 6.17 times 10 to the 14 reciprocal seconds, or hertz, is our frequency on this one. Any questions on that there? And again, since you do have a few options as to how to do it, they all should really get you to the same spot, as long as you obviously use the right form of the numbers in the calculation. All right, last one on this one here, similar to all those calculations you had to do on that last lab. N is equal to 3. N is equal to 2, I think. So initial and final, once again, we are dropping energy levels. So our change in energy minus 2.18 times 10 to the minus 18 joules, 1 over 2 squared minus 1 over 3 squared. And 1 divided by 4 minus 1 divided by 9 times 2.18 minus 18. Going to get us again a negative 3.03 times 10 to the minus 19 joules. Again, just like the other two, we are going from higher energy to lower. So we do expect a negative value here. Obviously, if we were doing the opposite transition here, maybe starting at 2 and ending at 3, we would get the same value for the energy, except it would be a positive number, right? So it'd be the same amount. It doesn't matter which way you're going for the electron, up or down. It's going to take the same amount of energy to do that transition either way. We'll go frequency here next. So the frequency going to be our E divided by H. Taking the positive value here. Those going to cancel, leaving us reciprocal seconds. So we'll end up here with, looks like a 4.57 times 10 to the 14 reciprocal seconds. And lastly, why not, for old time's sake, we'll go to this formula here to get to the wavelength. Wavelength is C divided by the frequency. So 3 times 10 to the 8 meters per second divided by 4.57 times 10 to the 14 reciprocal seconds. And that's going to get us here. Seconds are going to cancel, leaves us meters. We will end up with 6.57 times 10 to the minus 7 meters. Once again, converting that into nanometers. 10 to the minus 9 meters in a nanometer. Going to give us 657 nanometers, a little orangey red action happening perhaps at that point. Any questions on any of those calculations? We also see, hopefully, what we talked about in terms of waves, wavelength, energy, and also frequency. So our longest wavelength, right? We have 657 for this guy, 486 and 435. So this guy here is our longest wavelength, which means it should have the lowest energy, right? So we have 3.03 to the minus 19 on this guy. This guy is 435, which is our shortest wavelength, should have the higher energy. Since at 3.03, it has 4.58 times 10 to the minus 19. So again, more energy for that transition. as well. In addition, we should also have a lower frequency for this one, which has a longer wavelength. So we have 4.57 to the 14. If we roll back here to our shortest wavelength, which was our first transition we did, we had 6.9 times 10 to the 14. Again, a higher frequency, right? So all those things, you know, sort of fit to what we were talking about when we were talking about our waves, right? Longer wavelength, lower frequency, lower energy, shorter wavelength, higher frequency, higher energy. Any questions on that there? So it does look like our last one there was the longest wavelength, and obviously our first transition there resulted in the shortest wavelength. Obviously, you need to be able to do all those calculations. Any questions on that? And as you can see, there are multiple sort of pathways you can kind of get to the answer. And once again, they all should get you to the right answer if you choose and use the right numbers. Any questions? Good. Okay. All right. So as we kind of talked about there, before we kind of did those calculations, come back. There we go. There was this idea that, again, the Bohr modeled atom works really well to explain those four sort of colors and lines that we see in the hydrogen atom, but they do sort of fall apart as you move with more than one electron. So there was sort of a movement sort of away from Bohr's model through sort of experimentation later down the road. And one of the next things that sort of led us to this sort of modern atomic theory away from this quantum mechanical sort of theory versus Bohr's model of the atom was one that was done by de Broglie. And de Broglie actually didn't do any experiments. He actually just theorized it, and people did experiments later on and sort of backed up that it does seem plausible and good. He said that particles could have wave-like character, and again, it's that sort of dual nature we were talking about, that, you know, waves could have particle-like function, and particles, like an electron, also can carry wave-like function. So the idea there is de Broglie predicted that the wavelength of a particle is inversely proportional to its momentum. Because those particles are so small, the wave character of electrons is relatively significant, and you could calculate what is sometimes referred to as the de Broglie wavelength, which is this formula here in meters. H is our Planck's constant. This is the mass of the particle. It does need to be in kilograms. We're going to talk about why it needs to be in kilograms in just a second. And the velocity here of the particle in meters per second. Now, the reason why, for example, the mass here does need to be in kilograms has to do with H's units. When we have the units of H, it is joules times seconds. Now, if you remember, I think we saw at the very end of chapter 1, a joule is equal to a kilogram meter squared second squared. So that is the relationship we're actually using here. So if you substitute in this guy for the joule in that, we will end up with kilograms meter squared second squared times seconds. And that essentially is Planck's constants units, as this right here is basically a joule, divided by kilograms and divided by meters per second. So when we go through our sort of calculation here for the wavelength, the kilograms will cancel, hence why the mass needs to be in kilograms so that those cancel properly. 1 second here and 1 on the bottom will cancel out the seconds, and 1 meter here and 1 of those meters will cancel out, and that will again leave you meters for the wavelength in this case. The good news is it has no effect on the value of Planck's constant. It's still 6.63 times 10 to the minus 34. All you have to remember really when you use this equation is make sure this is in kilograms, the mass, so it properly cancels out. And the velocity also needs to be in meters per second. So if it happens to be in some other unit than meters per second, you need to kind of convert it to meters per second. Maybe if you had it in miles per hour or something like that, right? You got to do some conversions to get it to meters per second. So everything cancels out. All right, so let's take a look at one here. Let's calculate the de Broglie wavelength here for an electron that is traveling at 2.65 times 10 to the 6 meters per second. And the mass of an electron will go with 9.11 times 10 to the minus 31 kilograms. The back leaf of your book. So let's take a look at this one. So we're going to do the de Broglie wavelength, which is h divided by m times the velocity. Obviously, we have the mass is actually in kilograms, which makes it nice. We do have the velocity here. And obviously, again, h is Planck's constant, 6.63 times 10 to the minus 34 joules times seconds. Once again, the joule here is a kilogram meter squared second squared. It represents the same thing. So popping our number in here, we're going to go 6.63 times 10 to the minus 34. And we'll use the kilograms meters squared second squared so we can see that. In place of the joule, remember, we also do still have another seconds that's going to be multiplied there. Divided by our mass, 9.11 times 10 to the minus 31 kilograms, and our velocity, which is already in meters per second. Again here, second, going to take out both of them. Kilograms going to take out that one. And again, 1 meter on the bottom will take out one of the meters up on top. That is going to leave us just 1 meter left over. 6.63 to the minus 34 divided by 9.11 to the minus 31 divided by 2.65 to the 6 here. That's going to get us a wavelength of 2.75 times 10 to the minus 10 meters in this case. Yeah. Again, relatively small wavelength associated with this particle. Any questions on that calculation? And again, that is sometimes referred to as calculating the de Broglie wavelength. Yeah. Okay. All right, so So as we've been talking about, we are sort of moving away from Bohr's idea of this planetary model to this idea, which is again sometimes referred to as more quantum mechanical model. We really don't know how a particle like an electron is moving. And the next sort of idea that kind of moved us away from that was done by Heisenberg. And Heisenberg's uncertainty principle basically says those two things. There is a limitation to how much you know about, for example, how a particle like an electron, how it's actually moving and its position at the same time. In fact, the more you know about, for example, its location, the less you know about how it's sort of traveling and vice versa. So this is Heisenberg's uncertainty principle. The delta x there is the uncertainty in the particle's position. The delta mv is the uncertainty in its momentum, is equal to Planck's constant over 4 times pi. We're not going to really do any sort of calculations involving that, but that is one of the principles that tell us essentially, not like Bohr had it, where these electrons are traveling in these pretty little circles. It's pretty predictable, their path. We're kind of, again, moving away from that. This idea an electron like this particle here has a pretty random sort of movement, and we don't really know exactly at any given point in time where it's located or sort of how it got there. Yeah. That's exactly where we're heading. Exactly that. And again, that is where we're heading, and that's the idea of moving away from this sort of fixed idea of, like in Bohr's model, of these guys are in orbits and they're definitely going around, to this idea more of, well, there's a very high probability of where we could find an electron sort of moving around in an atom. And that is where we sort of transition from orbits to orbitals in this sort of quantum mechanical sort of theory. And one of the major things that sort of get us there is a guy by the name of Schrodinger. He had a lot of equations and wave functions that if you ever take physical chemistry, you'll do a bunch of those calculations. But essentially, the idea is what we were just talking about there a second ago. We're moving away from this sort of knowledge of, I think for sure, like it's in this orbit and it's super predictable. Like if I put my finger hypothetically on that orbit, eventually it'll come back around right and hit my finger because it's a sort of known pattern how the electron is moving. To this idea of the best we could do is go, well, I don't know how it got there. I don't know how it's moving, but I feel there's a very good high probability that there probably should be an electron in this sort of area of the atom. And one of the things that, we could kind of predict or sort of think of is we kind of know the features of the atom, which is it has a positive nucleus, right? So there should be, if you just think about it logically, a fairly high probability of finding an electron near the nucleus because of opposites attract, right? And this is one of the ideas like de Broglie and so forth, that particles, again, have this wave-like function, which again, like a guitar string, the particles could act like a standing wave, right? If you pluck a guitar string, right, you get a wave, but it's tied to the guitar, right? So the wave just doesn't go, the guitar string just doesn't fly off, right? And that's sort of the idea there. We have this attraction between the electrons, which are negatively charged, and the nucleus, which is positively charged. And ultimately, they're going to have this kind of wave function uh, characteristic that's going to kind of keep them tied together like a guitar standing sort of wave. By the way, when you have sort of a standing wave, there are areas where there's no amplitude. Those are sometimes referred to as nodes. And a lot of times we sort of vision the nodes in this sort of standing wave situation as sort of where we can kind of find the nucleus is sort of housed versus sort of the electrons out there kind of tied to it. So this is a probability sort of map of that for this transition from, as I mentioned before, moving away from orbits like we had in Bohr's model to this quantum mechanical model where we talk about orbitals, which are really just theoretical probability maps of, again, where you could find an electron within the atom. Again, even though it's a very high probability, based on Heisenberg's uncertainty principle, you don't know exactly where it's at or exactly how it got there. You just know, again, there should be a fairly good shot you could find that. Once again, as I just mentioned, we have our kind of positive nucleus there in the middle. Blue, not the best choice for that coloring in, I think. Okay, with a different color here, maybe. There we go. And again, you can kind of see the darker area of the blue, which is that sort of electron cloud and the electron density. And again, usually that indicates a higher probability. And as you sort of move away from the nucleus, you can kind of see it. I don't know how well on the screen you can, not too bad. You can kind of see again a little bit lighter as you move away from sort of where the nucleus would be. Again, that doesn't mean you can't find an electron out there. There's just again a lower probability of perhaps finding an electron out there versus near the nucleus. And again, that's what we see here. So we talk about orbitals, and they are difficult to define precisely, but orbital is a wave function. And we do picture orbitals in sort of 3 dimensions and as an electron density sort of map. And you may be familiar with, obviously, orbitals. And we're going to talk about them, obviously, here, like you did electron configuration. There are s orbitals, p orbitals, d orbitals, for example, and f orbitals. And let's take a look at each of those. So I'm just going to kind of skip ahead here. We'll come back to it here. Let me just find it real quick here, where I want to jump to first. So let's take a look at these different orbitals that you should probably be familiar with, I think. We'll go there. All right. So the first type of orbital are s orbitals. And s orbitals are basically just spheres. And by the way, when we talk about orbitals, as you may also perhaps remember, any individual orbital could hold a maximum of 2 electrons. So any individual orbital could hold a maximum of 2 electrons. This is a 1s orbital. That means it's basically on the first energy level. That's a 2s orbital, which means it's basically on the second energy level. That's a 3s orbital, which basically is on the third energy level. So they're all spheres. They're all, again, gets larger as they go from different energy levels to accommodate all the electrons that are there. And again, you can visualize that perhaps the nucleus is sort of in the center there. And again, that is going to be probably your area of highest sort of electron density.
An s orbital has a spherical shape with the nucleus at the center.
And the next type of orbitals are actually p orbitals. And p orbitals, there's actually 3 types of p orbitals. By the way, for s orbitals, there's only one type of s orbital. And there are what is referred to as the px orbital, the py orbital, and the pz orbital on the different axes there. And they're sometimes described as sort of like a figure 8 type of deal, where we have sort of this node in the middle, where we could kind of assume, again, the nucleus is highest probability, again, of finding electrons kind of in that area on each of those lobes. Electrons could be on either side of those 3-dimensional fake, never going to see them from real life in an atom type of orbitals here, probability type maps. Now, one of the things that we sometimes come across is when you have more than one orbital on the same energy level, that's the same type of orbital. This is sometimes, if you take all 3 of these orbitals together, this is sometimes referred to as the 2p subshell or sub-level, depending on your book. And it's a 2p because we happen to be on the second energy level here, and is equal to 2 in this case. And if you were to, for example, fill up the entire p subshell, as you may know, that would then mean you can max out at 6 electrons, right? So if you filled up the entire p orbital, they're made up of 3 individual p orbitals, each equal to 2. You could put 6 electrons on a p subshell on a particular energy level. Now, here's what they kind of look like.
The 2px orbital is in the shape of a figure 8 along the x-axis.
And the y, it's kind of the same deal.
The 2py orbital is in the shape of a figure 8 along the y-axis.
And then our z.
The 2pz orbital is in the shape of a figure 8 along the z-axis.
Now, the next set of orbitals where we sort of can find electrons in the atom are d orbitals. And there's actually 5 different types of d orbitals, as you can see in these pictures. They essentially, for the most part, look like 2p orbitals have been stuck together, except for this one, classically called a donut with a p orbital in the middle of it. As you can see here, these are, again, just basically theoretical electron density maps, thinking the nucleus is somewhere in this region. Again, you can see the higher probability of finding an electron is going to be, again, near that nucleus. As you sort of fan out away from it, not as many dots, not as much density of electrons in that particular area. Same thing for the rest of them. Once again, if you took all 5 of these d orbitals together, this would be the d subshell in this particular case. And if you max out the electrons in this, you would be able to put 10 electrons total, again, 2 into each of these orbitals. The next sort of orbitals that you're probably familiar with, well, we'll take a look at a couple of these.
X squared minus y squared orbital has a cloverleaf shape that lies in the xy plane and is aligned along the x and y axes.
We won't look at all of them. I think go with that guy.
The 3dxz orbital has a cloverleaf shape that lies in the xz plane and bisects the x and the z axes.
Your donut.
The 3dz squared orbital is shaped like a pz orbital with a donut of electron density around the center. It is aligned with the z-axis.
The last type of orbitals, again, that you're familiar with, probably is the f orbitals, and there's actually 7 types of f orbitals. And as you can see here, there's sort of like some D's put together. They are, if you take all 7 of these guys together, that's going to give you a subshell or sublevel, and that's the F subshell or sublevel. And obviously you would max out in terms of electrons in this case with 14 electrons, again 2 in each of these guys. All right, so again, these orbitals are sort of what we move to away from Bohr's model into this quantum mechanical model of, hey, this is electron density, they're going to be sort of in here. Will you actually see these type of shapes? No, they're again just really calculation theoretical sort of maps a probability of where you can find an electron. Again, you'll do those calculations if you ever take PChem, you know, this is sort of what we visualize sort of what they will be in or where you can find them. All right, so let's go back to sort of what we skipped, which basically is now going to explain why we have all these orbitals, right? And why, you know, on certain energy levels, there's only this type of orbitals present. On other energy levels, there are different orbitals present. So let's get into the part of the class everybody loves. Just kidding. Maybe, maybe not. I don't know. Right here, where's that slide? Go there. All right, so we're now going to talk about quantum numbers, and there actually are 4 types of quantum numbers. And you might have learned about one, which is the N, and we also talked about it earlier. And it's a principal quantum number, and it is basically the size and energy of the orbital. For lack of a better description, it is basically the energy levels, as we talked about. N could have values of 1 through 7. And as we talked about earlier, N equals 1 is the ground state. That, again, is the lowest energy you could have, closest to the nucleus. Everything above that is, again, considered an excited state. And once again, that means it's higher in energy and further away from the nucleus. The next quantum number is what is known as the angular momentum quantum number. It is L. And it is basically the shape of the atomic orbital. Again, for just a regular description of really what it tells you what type of orbital you're dealing with. Are you dealing with an s orbital? Are you dealing with a p orbital? Are you dealing with like a d orbital and so forth? Now, L could have values of 0 to n minus 1. So it could run kind of whole numbers from 0 to n minus 1, n being, of course, the principal quantum number above that we just talked about. The next sort of quantum number is the magnetic quantum number, m sub L. That's basically the orientation of these orbitals in 3-dimensional space. Again, just a straight up, what will actually sort of tell you, if you want to kind of look at it, it will actually tell you how many individual orbitals you have for a particular type of orbital, like how many individual d orbitals there are, or how many individual p orbitals there are in a subshell. The last one, which is down the road there, I'm not sure why I got sort of moved, is the spin quantum number. The spin quantum number is m sub s, and this is obviously m sub L. And the spin quantum number basically could have 1 of 2 values. It could either be plus a half or minus a half. And sometimes people put it together plus or minus a half. And the spin quantum number tells you the spin of the electron within the orbital. And the electron has its own spin. It's affected by electrical field, magnetic field. Typically speaking, when we say the spin quantum number is plus 1/2, it is represented as the electron is spinning sort of upwards, if you will, or if you're going to represent the electron with an arrow, it's going to be pointing in the upwards direction. If we say the spin quantum number for that electron is minus 1/2, it essentially means sort of the opposite spin is going to kind of be pointing downward, if you will, and that would be minus half. These are the 4 quantum numbers, which essentially, as you go through them, and we're going to go through them so you can kind of see how they relate to our orbitals and why things happen on certain energy levels. They basically account for, again, why we see certain orbitals on certain energy levels and maybe not on other energy levels, and why we have, how many of these orbitals in these subshells. So let's take a look and see how we could kind of go through this here. And we'll come back to that, I think. There we go. This will work, that page here. So why don't we just start with n equals 1? Seems like a good place to start. If n is equal to 1, that is obviously the first energy level. Now, when we look at L can have values, as I mentioned, of 0 to n minus 1, which means in this case, if n is equal to 1, 1 minus 1 is 0, right? So the only value that you could have in an n is equal to 1 for L is 0. Now, why is that important? When you have an L value of 0, it represents our friend, the s orbital. Yeah. So when you have a 0 for L, it represents the s orbital. What does that mean? That means when I roll down here to my n equals 1 level, the absolute only orbital that's present is a 1s orbital, because quantum numbers tell us that's the only acceptable orbital that can be found on the energy level. So on the very first energy level, there is no other orbitals present, because the only allowable orbital is the s orbital based on the quantum numbers. Now, when I do m sub L, which is the angular momentum quantum number, or I'm sorry, the magnetic quantum number, that has values, I didn't really put it on the last slide, but let me put it here. It has values of minus L to 0 to plus L. So these are the acceptable values for m sub L. In this particular case, because my L value is 0, you can't have negative 0, right, or so forth. The only value I could have for m sub L on the first energy level is 0. And you could have an m sub L for every L value that you have. So since we only have the 0, the only possible one is m sub L of 0. Essentially what that means is I got myself one s orbital available to me. And that's basically what that 0 represents. The last quantum number here is the spin quantum number, and that could be plus or minus 1/2. What that essentially tells us when we go through our first energy level and the 4 quantum numbers associated with the first energy level, it tells us that on the first energy level, the only orbital we could have is an s orbital. There's actually only one s orbital available. And if I put electrons into that s orbital, I could only put a maximum of 2 electrons into that s orbital, one going upwards and one going downward, if you will. Any questions on that there? Now, what happens when we get to the second energy level? If n is equal to 2, what are all the values I could possibly have for L in this case? L could be, it runs from 0 to n minus 1, right? So in this case, n minus 1 is equal to 1, right? 2 minus 1 is 1. So it could have a value of 0. It could also have a value of 1 in this case, by taking 2 minus 1 gives us 1. We already know what that tells us for the 0. That means that when I come to my second energy level, I have L is equal to 0, which means that should be a s orbital present, and that is known as a 2s orbital, right? So that is why we have a 2s orbital also present on the second energy level. Maybe you could guess, but an L value of 1 actually equals a p orbital. So this is why we don't see p orbitals until we get to the second energy level, because based on quantum numbers, they cannot appear until you get to the second energy level. Now, for each of these L values, where we have, I'll go this way, we have an L is equal to 0, we could do an m sub L like we did above. So our m sub L is 0, which means we will only have our one s orbital at this point. I could also do my L value here of 1. What would my m sub L be for that? It runs from minus L to 0 to plus L. So L in this case is 1, so minus L would be -1, right, to 0, to plus L, which would be +1. That is the 3 acceptable values for our p orbitals, and that is -1, 0, and +1. By the way, how many p orbitals are there in a subshell? P orbitals, there are 3, yeah? And how many numbers do I have here? 1, 2, and 3. Each of those numbers represents a different p orbital. Hence, we go 1, 2, 3 for our 2p's. By the way, this is the px orbital, the py orbital that we saw in those little videos, and that would be our pz orbital, and that is basically what they represent. Now, for each of these, again, in those orbitals, we could have an electron that is pointing upwards or downwards for our spin quantum number, plus or minus a half, right? So the quantum numbers here, as you can see, is really the basis of why you were told when you did electron configuration, hey, p orbitals don't show up to like the second energy level, right? On the first energy level, you only have s's. Any questions on that there? So why don't you try this one? Why don't you do n is equal to 3, the third energy level? Why don't you figure out all the L values you could have, and for each L value, figure out what the M sub L values are and the MS values. So take a moment there and okay, so getting to the end here. Take a look at it here and see. So if we're going to start on the third energy level, that's going to give us some possible values of L. And again, L is 0 to n minus 1. So if n is 3, n minus 1 is 2. That means for L, we could have 0, 1, and 2. We've already seen that an L value of 0 is the s orbital. A L value of 1 is the p orbital. And you might guess that the L value of 2 represents the d orbitals in this particular case. Now, we can, for this guy here, just like we did previously, our M sub L will also still be 0, which means on the third energy level, we have s orbitals, which is a 3s orbital. We have one 3s orbital that can have electrons that are either spinning up or down. For our p, just like we did on the previous slide there, we could have an M sub L of -1 to 0 to +1, which again tells us on the third energy level, we have p orbitals present. We have our 3 p orbitals, px, py, and pz present here based on our M sub L. And each of those orbitals can have an electron that's either pointing upwards or downwards, or spinning up or spinning down. Now, the one that we just got here that is new tells us that when we reach our third energy level, we will actually see some d orbitals. And our M sub L for that, again, is going to run from negative L to positive L. So that would give us a -2, -1, 0, +1, and +2. By the way, d orbitals, there's how many of them? 5. 1, 2, 3, 4, and 5. So again, each of those M sub L values represent one of the 5 d orbitals. And each of them can have a spin quantum number plus or minus a half. Again, an electron going upwards or downwards in there. So the picture that we're seeing here based on quantum numbers is, as we saw on the very first energy level, based on quantum numbers, we basically only have an s orbital available to us. When we reach the second energy level, we still have an s orbital available, which is known as a 2s orbital. And that's where we first have available to us our p orbitals. Now that we get to our third energy level, we still see the s orbital. We still see the p orbitals, which are the 3p. And now we have the introduction on the third energy level of our d orbitals, which there are 5 of them as well. Question on how quantum numbers tie into why we have these orbitals on the different energy levels here. Once again, as we talked about before, this grouping here would be considered a subshell, right? So with this, And also, so with that, right, a subshell. Again, for the S's, because they only have one orbital, they're not considered a subshell. They're just considered an S orbital. Any questions on that there? All right, we will lay it up there for today.